In this new course, we're going to look at advanced circuit analysis, which is kind of piggybacking the circuit analysis course that we previously had. The link for that playlist will be in the description. So a lot of the techniques used in that course are also used in this course, which is kind of a next level up for more complex systems. And picking up where we left off in the last course, we're going to look at AC circuit analysis, where we looked at power, all the different kinds of power, complex, apparent, average, all that fun stuff. And that'll bridge us into three-phase systems, where we will look at what they are, how they can be configured, and all the properties of three-phase systems. Following that, we will look at transformers. And from that, we'll look at transient responses of circuits, which will be coupled with S-domain or Laplace transform circuits. And with all of that information, we can then investigate frequency responses of circuits. And lastly, we'll look at two-port networks, what they are, why they're useful, and how to analyze them. So as a slight recap, we're just going to look at instantaneous power. Now recall that power is defined as the current times the voltage. And if we consider a current given by some magnitude Im, and then we have a cosine omega t plus theta I, where omega is your angular frequency and theta I is your phase, then if we have a similar representation of the voltage, we can multiply these two together to get the instantaneous power. Now we're going to use the trig identity of cosine of A multiplied by cosine of B, gives us this term here where we have a cosine of A plus B plus cosine of A minus B divided by 2. And if we do that for the current and the voltage, which are time dependent, we get an instantaneous power that looks like this, where you can see you have a time independent contribution and a time dependent contribution. And if you plot this, you get the graph on the right, or horizontally we're looking at time. And what you can see is you have this oscillatory instantaneous power. Now, if you take the average of this function, you essentially get 1/2 multiplied by the amplitudes of the voltage and the current, and then you get cosine of the difference, or the voltage and the current. And just referring back to our standard convention, where if we have the power greater than 0, it's absorbed by some element of the circuit, and if it's less than 0, it's absorbed by the source. So mathematically, we can also define the average power as an integral, and that integral is given by 1 divided by t, where t is the time period, and then we have the integral 0 to t with that time-dependent power, then with respect to time. So one of the reasons that we care about the average power is that it's simply easier to measure on a device. But carrying through with that integral, where we have our time-independent contribution and our time-dependent contribution, we're left with two integrals to evaluate. And simply recall that that time period t is the reciprocal of frequency, so 1/f. And omega is our angular frequency, which is equal to 2 pi times the frequency. So then this second contribution of the integral simply becomes this evaluated, which gives us 0. So then we're just left with the average power and that time independent contribution, and that gives us what we arrived at before. So we also introduced phasors in the circuit analysis course, and in the phasor domain, the power is given by 1/2 times the real part of the voltage multiplied by the conjugate of the current. And recall, if the current is given by some complex number, A plus JB, the conjugate is equal to A minus JB. Now we also have RMS values, root mean square, or effective values. And for an AC circuit, it gives us the DC equivalent that delivers the same average power. So in our AC circuit, we had the average power equal to this term right here from above. And we want to convert that to some DC circuit, where we have the average power equal to the RMS voltage times the RMS current. Now to actually get these RMS values, we have another equation where, again, it's an integral, except we have this square root over the top of it. And then inside the square root, we have 1 over t, the integral 0 to t. We have x of t squared with respect to time. And for simplicity, if we consider a current that has a phase angle of 0, we arrive at this integral here. We can simply use another trig substitution for that cosine squared term, and that gives us two integrals. Again, we have a time independent and a time dependent contribution. So the time dependent contribution will evaluate to 0, and we're just left with the time independent contribution here. And all of this is under that square root term. So we can say that I RMS is equal to the square root over the magnitude of that current squared divided by 2. And that's going to be equal to the magnitude of the current divided by the square root of 2. Similarly, if we did this for the voltage, we would get the magnitude of the voltage and then the square root of 2. And then again, kind of recapping everything that we looked at in the circuits analysis course, we have a lot of different terms for power. We have the apparent power, which is equal to the RMS voltage times the RMS current, and the unit for that is going to be the volt amp. So if we have some voltage and some current with respective phase angles, we can simply say that the average power is equal to V RMS times I RMS, and then we have this cosine term here. And we know that the V RMS and I RMS is going to be equal to the apparent power. So we're just left with the apparent power times this cosine of theta V minus theta I. And that cosine term is what we define as the power factor, which you could say is equal to the average power divided by the apparent power. So inside this cosine term, we have theta V minus theta I, which is our phase difference between the voltage and the current. And this is what we call our power factor angle. So if the difference between them is negative, we say that the power factor is leading, which means the current leads the voltage. And if it's greater than 0, that power factor is lagging, and the current lags the voltage.